Learning objectives. In this chapter, the user would learn the following in detail: data link layer function, switching process, Ethernet standard and its various frame formats, CAM table, hardware address or physical addresses, DTP, VLAN, VTP, VLAN routing, STP, WAN links, serial links, L2 WAN protocols, PPP, PPP authentication protocol like PAP and CHAP, frame relay and standard HDLC protocols. CAM table. The CAM table is one of the fundamental operations of a switch. The CAM table or content addressable memory table is present for layer 2 switching. A forwarding information base or FIB is also known as a forwarding table or CAM table, is most commonly used in network bridging, routing and similar functions to find the proper interface to which the input interface should forward a packet. It is a dynamic table that maps MAC addresses to ports. It is the essential mechanism that separates network switches from network hubs. An Ethernet switch's role is to copy Ethernet frames from one port to another. The presence of a CAM table is one attribute that separates a switch from a hub. Without a functional CAM table, all frames received by a network switch would be echoed back out to all other ports, much like an Ethernet hub. A switch should only emit a frame on the port where the destination network device resides, or unicast, unless the frame is for all nodes on the switch or broadcast, or multiple nodes or multicast. Generally, the CAM table is a system memory construct used by Ethernet switch logic to map a station's MAC address to the switch port the station is connected to. This allows switches to facilitate communications between connected stations at high speed regardless of how many devices are connected to the switch. The CAM table is consulted to make the frame forwarding decision. Switches learn MAC addresses from the source address of Ethernet frames on the ports, such as Address Resolution Protocol response packets. The CAM table is used in multi-layer switching for the purpose of quickly switching frames to their destination. The switch looks at the incoming frame's source MAC address and enters it into the CAM table and keeps it there for 300 seconds before aging out. This is the default value. If the device connected to that switch port is moved to another port, the switch records the incoming source MAC address, updates the CAM table and removes its previous entry for the same MAC address. Host A is connected to switch port 1 and host B is connected to switch port 2. Host A sends traffic to the switch. The switch looks into the frame and records the source MAC address of host A and places an entry into the CAM table. Host A is on switch port 1, has the MAC address of AAAA, VLAN D ID of 1 and the timestamp. Host B has not communicated with the switch yet. Host A decides to communicate with host B. When host A sends a frame to the switch destined to host B, the switch notices the destination MAC address for host B in the frame, queries the CAM table for that MAC address but doesn't find it. Because the destination MAC is unknown, the switch marks the frame for flooding and sends the unicast frame to all ports with the same VLAN association. Host B responds to the unicast frame. The switch records the incoming frame from host B and records host B's MAC, switch port location, VLAN ID and applies a timestamp. The next time host A sends a frame destined for host B, the switch queries its CAM table, finds host B in the table and sends the frame directly to host B. CAM table before host B communicates on the network. Open square bracket, table ID equal to 1 / close square bracket, CAM table after host B communicates on the network. Open square bracket, table ID equal to 2 slash close square bracket. DTP. The Dynamic Trunking Protocol or DTP is a proprietary networking protocol developed by the purpose of negotiating trunking on a link between two VLAN aware switches and for negotiating the type of trunking encapsulation to be used. It works on layer 2 of the OSI model. VLAN trunks formed using DTP may utilize either IEEE 802.1q. DTP involves with trunk port establishment and protocol transmits the data frame that trunks carry. DTP datagrams are also sent if the port is set statically to the trunk mode. However, both sending and processing DTP datagrams are deactivated when the port is set statically to the access mode. The following switch port mode settings exist. Access puts the Ethernet port into permanent non-trunking mode and negotiates to convert the link into a non-trunk link. The Ethernet port becomes a non-trunk port even if the neighboring port does not agree to the change. Trunk puts the Ethernet port into permanent trunking mode and negotiates to convert the link into a trunk link. The port becomes a trunk port even if the neighboring port does not agree to the change. Dynamic Auto makes the Ethernet port willing to convert the link to a trunk link. The port becomes a trunk port if the neighboring port is set to a trunk or dynamic desirable mode. This is the default mode for all Ethernet ports. Dynamic desirable makes the port actively attempt to convert the link to a trunk link. The port becomes a trunk port if the neighboring Ethernet port is set to trunk, dynamic desirable or dynamic auto mode. Negotiate disables DTP. The port will not send out DTP frames or be affected by any incoming DTP frames. If you want to set a trunk between two switches when DTP is disabled, you must manually configure trunking using the switch port mode trunk command on both sides. The individual combinations of port and equivalent settings are as follows. Dynamic auto plus dynamic auto equals to access. Dynamic auto plus dynamic desirable equals to trunk. Dynamic desirable plus dynamic desirable equals to trunk. Dynamic auto or dynamic desirable plus trunk equals to trunk. Dynamic auto or dynamic desirable plus access equals to access. If both ports are dynamic auto, they will act as access ports. If either of them is dynamic desirable, both will agree on trunking. If one of them is dynamic and the other is static, the mode is dictated by the statically set port. The DTP protocol is unauthenticated, which means that a station can send false DTP packets pretending to be a switch. If the switch port is configured as a dynamic port, an attacker can lure the switch port to become a trunk port and he will gain access to all VLANs allowed on a trunk. Therefore, after a network has been installed, it is the best practice to set the mode statically and deactivate the DTP protocol on a port using the command switch port no negotiate. Data link layer function. Data link layer. Data link layer is second layer of OSI layered model. This layer is one of the most complicated layers and has complex functionalities and liabilities. Data link layer contains the details of underlying hardware and functions itself as the medium for communication between upper layers. Data link layer works between two hosts which are directly connected in some cases. This direct connection might be point-to-point or broadcast. Systems on broadcast network are said to be on same link. The work of data link layer tends to get more complex when it is dealing with multiple hosts on single collision domain. Data link layer is responsible for converting data stream to signals bit by bit and to send that over the underlying hardware. At the receiving end, data link layer picks up data from hardware. which are in the form of electrical signals, and assembles them in a recognizable frame format. Finally, hands over to the upper layer. Data link layer has two sublayers. Logical link control. It deals with protocols, flow control, and error control. Media access control. It deals with actual control of media. Functionality of data link layer. Data link layer does many tasks on behalf of upper layer. These are framing, addressing, synchronization, that is access control, error control, flow control, multi-access. Framing. Data link layer takes packets from network layer and encapsulates them into frames. Then it sends each frame bit by bit on the hardware. At receiver's end, data link layer picks up signals from hardware and assembles them into frames. A frame is a digital data transmission unit in computer networking and telecommunication. A frame typically includes frame synchronization features, consists of a sequence of bits or symbols that indicate to the receiver the beginning and the end of the payload data within the stream of symbols or bits it receives. If a receiver is connected to the system in the middle of a frame transmission, it ignores the data until it detects a new frame synchronization sequence. In the OSI model of computer networking, a frame is the protocol data unit at the data link layer. Frames are the result of the final layer of encapsulation before the data is transmitted over the physical layer. A frame is the unit of transmission in a link layer protocol and consists of a link layer header followed by a packet and the trailer at the end. Each frame is separated from the next by an interframe gap. A frame is a series of bits generally composed of framing bits, the packet payload, and a frame check sequence. Examples are Ethernet frames, point-to-point protocol or PPP frames, fiber channel frames, and V.42 modem frames. In telecommunications, a frame is data that is transmitted between network points as a unit complete with addressing and necessary protocol control information. A frame is usually transmitted serial bit by bit and contains a header field and a trailer field that frame the data. Some control frames contain no data. Flag 01111110 and address field comes under header, then information or data field which is 0 to 4096 bytes. Frame sequence check sequence and flag 01111110 comes under trailer. In the figure above, the flag and address fields constitute the header. The frame check sequence and second flag fields constitute the trailer. The information or data in the frame may contain another encapsulated frame that is used in a higher level or different protocol. In fact, a frame relay frame typically carries data that has been framed by an earlier protocol program. In the time division multiplexing or TDM, a frame is a complete cycle of events within the time division period. Addressing. Data link layer provides layer 2 hardware addressing mechanism. Hardware address is assumed to be unique on the link. It is encoded into hardware at the time of manufacturing. Data link layer or DLL provides addressing scheme that is used in transporting the frame across the local shared media. The device address in this layer is called the physical address. Data link layer divides the packets and makes the frames. Data link layer frame contains the frame header. The header can also contain the source address of the frame. Unlike layer 3 logical addresses that are hierarchical, physical address does not indicate on what network the device is located. If the device is moved to another subnet, it will still function with the same layer 2 physical address. Because the frame is only used to transport data between nodes across the local media, the data link layer address is only used for local delivery. Addresses like this layer have no meaning beyond the local network. Compare this to layer 3, where addresses in the packet header are carried from source host to destination host regardless of the number of network hops along the route. If the packet in the frame must pass on to another network segment, the intermediate device, a router, will decapsulate the original frame, create a new frame for the packet, and send it onto the new segment. The new frame will use source and destination addressing as necessary to transport the packet across the new media. Addressing requirements. The need for data link layer addressing at this layer depends on the logical topology. Point-to-point topologies with just two interconnected nodes do not require addressing. Once on the medium, the frame has only one place it can go. Because ring and multi-access topologies can connect many nodes on a common medium, addressing is required for these topologies. When a frame reaches each node in the topology, the node examines the destination address in the header to determine if it is the destination of the frame. Data link layer protocols add a trailer to the end of each frame. The trailer is used to determine if the frame arrived without error. This process is called error detection. Note that this is different from error correction. Error detection is accomplished by placing a logical or mathematical summary of the bits that comprise the frame in the trailer. Frame check sequence. The frame check sequence or FCS field is used to determine if errors occurred in the transmission and reception of the frame. Error detection is added at the data link layer because this is where data is transferred across the media. Synchronization. When data frames are sent on the link, both machines must be synchronized in order to transfer to take place. Beginning and end of the frames need to be detected by the special synchronization fields called flag fields. It may exist for both parts, also may use interframe transmission gap instead of end flag. The 4-frame synchronization are follows. Character count, starting and ending characters with character stuffing, starting and ending flags with bit stuffing, physical layer coding violations. Character count. This method uses a field in the header to specify the number of characters in the frame. When the data link layer at the destination sees the character count, it knows how many characters flow and hence where the end of the frame is. The disadvantage is that if the count is garbled by a transmission error, the destination will lose synchronization and will be unable to locate the start of the next frame, so this method is rarely used. Character stuffing. In the second method, each frame starts with the ASCII character sequence DLE STX and ends with the sequence DLE ETX, where DLE is data link escape, STX is start of text, and ETX is end of text. This method overcomes the drawbacks of the character count method. If the destination ever loses synchronization, it only has to look for DLE STX and DLE ETX characters. If, however, binary data is being transmitted, then there exists a possibility of the characters DLE STX and DLE ETX occurring in the data. Since this can interface with the framing, a technique called character stuffing is used. The sender's data link layer inserts an ASCII DLE character just before the DLE character in the data. The receiver's data link layer removes before this data is given to the network layer. However, character stuffing is closely associated with 8-bit characters, and this is a major hurdle in transmitting arbitrary sized characters. Bit stuffing. The third method allows data frames to contain an arbitrary number of bits and allows character codes with an arbitrary number of bits per character. At the start and end of each frame is a flag byte consisting of the special bit pattern 01111110. Whenever the sender's data link layer encounters 5 consecutive ones in the data, it automatically stuffs a 0 bit into the outgoing bit stream. This technique is called bit stuffing. When the receiver sees 5 consecutive ones in the incoming data stream, followed by a 0 bit, it automatically destuffs the 0 bit. The boundary between the two frames can be determined by locating the flag pattern. Physical layer coding violations. The final framing method is physical layer coding violations and is applicable to networks in which the encoding on the physical medium contains some redundancy. In such cases, normally a 1 bit is a high-low pair and a 0 bit is a low-high pair. The combinations of low-low and high-high which are not used for data may be used for marking frame boundaries. Error control. Sometimes signals may have encountered problem in transition and the bits are flipped. These errors are detected and attempted to recover actual data bits. It also provides error reporting mechanism to the sender. Network is responsible for transmission of data from one device to another device. The end-to-end transfer of data from a transmitting application to a receiving application involves many steps, each subject to error. With the error control process, we can be confident that the transmitted and received data are identical. Data can be corrupted during transmission. For reliable communication, error must be detected and corrected. Error control is the process of detecting and correcting both the bit level and packet level errors. Types of errors. Single bit error. The term single bit error means that only one bit of the data unit was changed from 1 to 0 and 0 to 1. Burst error. In term burst error means that the two or more bits in the data unit were changed. Burst error is also called packet level error, where errors like packet loss, duplication, reordering. Two basic approaches to handle bit errors are error correcting and codes and error detecting codes plus retransmission. Error detection. Error detection is the process of detecting the error during the transmission between the sender and the receiver. Types of error detection. Parity checking, cyclic redundancy check or CRC, checksum. Redundancy. Redundancy allows a receiver to check whether received data was corrupted during transmission, so that he can retransmission. Redundancy is the concept of using extra bits for use in error detection. As shown in the figure, sender adds redundant bits R to the data unit and sends to receiver, when receiver gets bit stream and passes through checking function. If no error, then data portion of the data unit is accepted and redundant bits are discarded. Otherwise, asks for the retransmission. Parity checking. Parity adds a single bit that indicates whether the number of 1 bits in the preceding data is even or odd. If the single bit is changed in transmission, the message will change parity and the error can be detected at this point. Parity checking is not very robust, since if the number of bits changed is even, the check bit will be invalid and the error will not be detected. Number 1. Single bit parity. Number 2. Two-dimension parity. Moreover, parity does not indicate which bit contained the error. Even when it can detect it, the data must be discarded entirely and retransmitted from scratch. On a noisy transmission medium, a successful transmission could take a long time or even never occur. Parity does have the advantage, however, that it's about the best possible code that uses only a single bit of space. Cyclic redundancy check. CRC is a very efficient redundancy checking technique. It is based on binary division of the data unit, the remainder of which CRC is added to the data unit and sent to the receiver. The receiver divides data unit by the same divisor. If the remainder is 0, then data unit is accepted and passed up the protocol stack. Otherwise, it is considered as having been corrupted in transit, and the packet is dropped. Sequential steps in CRC are as follows. Sender follows following steps. Data unit is composite by number of zeros, which is one less than the divisor. Then it is divided by the predefined divisor using binary division technique. The remainder is called CRC. CRC is appended to the data unit and is sent to the receiver. Receiver follows following steps. When data unit arrives followed by the CRC, it is divided by the same divisor which was used to find the CRC remainder. If the remainder result in this division process is 0, then it is error-free data, otherwise it is corrupted. Checksum. Checksum is the third method for error detection mechanism. It is used in the upper layers, while parity checking and CRC is used in the physical layer. Checksum is also on the concept of redundancy. In the checksum mechanism, two operations to perform. Checksum generator. Sender uses checksum generator mechanism. First data unit is divided into equal segments of n bits. Then all segments are added together using 1's complement, then its complements once again. It becomes checksum and sends along with data unit. Example, if 16 bits 1000, 1010, 001, 00011 is to be sent to receiver, so the checksum is added to the data unit and sent to the receiver. Final data unit is 1000, 1010, 001, 00011, 0101, 0000. Checksum checker. Receiver receives the data unit and divides into segments of equal size of segments. All segments are added using 1's complement. The result is completed once again. If the result is 0, data will be accepted, otherwise rejected. Example, the final data is non-zero, then it is rejected. Error correction. Error correcting codes are used if retransmission of the data is not possible. Data are encoded with sufficient redundancy to correct bit errors. Examples, Hamming codes, Reed-Solomon codes, etc. This error control allows to reconstruct the original information when it has been corrupted during transmission. Hamming code. It is a single bit error correction method using redundant bits. In this method, redundant bits are included with the original data. Now, the bits are arranged that different incorrect bits produce different error results and correct bit can be identified. Once the bit is identified, the receiver can reverse its value and correct the error. Hamming code can be applied to any length of data unit and uses the relationships between the data and the redundancy bits. Algorithm. Parity bits are positions at the power of 2 or 2r. Rest of the positions is filled by the original data. Each parity bit will take care of its bits in the code. Final code will be sent to the receiver. In the above example, we calculate the even parities for the various bit combinations. The value for each combination is the value for the corresponding R, that is redundancy bit. R1 will take care of bit 1, 3, 5, 7, 9 and 11, and it is set based on the sum of even parity bit. the same method for rest of the parity bits. If the error occurred at bit 7, which is changed from 1 to 0, then receiver recalculates the same sets of bits used by the sender. By this we can identify the perfect location of error occurrence. Once the bit is identified, the receiver can reverse its value and correct the error. Flow control. Stations on the same link may have different speed or capacity. Data link layer ensures flow control that enables both machines to exchange data on same speed. Flow control is one important design issue for the data link layer that controls the flow of data between sender and receiver. When sender sends data to receiver, then there can be problem in below case. Number 1. Sender sends data at higher rate and receive is too sluggish to support that data rate. To solve the above problem, flow control is introduced in data link layer. It also works on several higher layers. The main concept of flow control is to introduce efficiency in computer networks. Approaches of flow control. Number 1. Feedback-based flow control. Number 2. Rate-based flow control. Feedback-based flow control. Feedback-based flow control is used in data link layer and rate-based flow control is used in network layer. In feedback-based flow control, until sender receives feedback from the receiver, it will not send next data. Types of feedback-based flow control. A. Stop and wait protocol. B. Sliding window protocol. Number 1. A 1-bit sliding window protocol. Number 2. A protocol using go back N. Number 3. A protocol using selective repeat. A. A simplex stop and wait protocol. In this protocol we have taken the following assumptions. Number 1. It provides unidirectional flow of data from sender to receiver. Number 2. The communication channel is assumed to be error-free. In this protocol, the sender simply sends data and waits for the acknowledgement from receiver. That's why it is called stop and wait protocol. This type is not so much efficient, but is the simplest way of flow control. In this scheme, we take communication channel error-free, but if the channel has some errors, then receiver is not able to get the correct data from sender, so it will not be possible for sender to send the next data because it will not get acknowledgement from the receiver. So it will end communication. To solve this problem, there are two new concepts were introduced. Timer. If sender was not able to get acknowledgement in the particular time, then it sends the buffered data once again to receiver. When sender starts to send the data, it starts timer. Sequence number. From this, the sender sends the data with the specific sequence number, so after receiving the data, receiver sends the data with that sequence number, and here at sender side it also expects the acknowledgement of the same sequence number. This type of scheme is called positive acknowledgement with retransmission or PAR. Sliding window protocol. Problems stop-wait protocol. In the last protocol, sender must wait for either positive acknowledgement from the receiver or for timeout to send the next frame to receiver. So if the sender is ready to send the new data, it cannot send. Sender is dependent on the receiver. Previous protocols have only the flow of one-sided, means only sender sends the data and receiver just acknowledges it. So the twice bandwidth is used. To solve the above problems, the sliding window protocol was introduced. In this, the sender and receiver both use buffer. It's of same size, so there is no necessary to wait for the sender to send the second data. It can send one after the another without wait of the receiver's acknowledgement. And it also solves the problem of using of more bandwidth, because in this scheme both sender and receiver uses the channel to send the data and receive just to send the acknowledgement which it want to send to sender. So there is no special bandwidth used for acknowledgement. So the bandwidth is saved, and this whole process is called piggybacking. Types of sliding window protocol. 1. A 1-bit sliding window protocol. 2. A protocol using go back N. 3. A protocol using selective repeat. Sliding window protocol. The window size at the receiver end may be large or only of 1. In the case of window size is 1 at the receiver. If sender wants to send the packet from 1 to 10, but suppose it has error in second packet, so sender will start from 0, 1, 2, etc. Here we assume that sender has a timeout interval with 8. So the timeout will occur after the 8 packets. Up to that, it will not wait for the acknowledgement. In this case, at the receiver side, the second packet come with error, and other up to 8 were discarded by receiver. So in this case, the loss of data is more. Whether in the other case with the large window size at receiver end, if the second packet comes with error, then the receiver will accept the third packet, but it sends NAK of 2 to the sender and buffer the third packet. Receiver do the same thing in fourth and fifth packet. When the sender receives the NAK of second packet, it immediately sends the second packet to the receiver. After receiving the second packet, receiver sends the ACK of the fifth as saying that it has received up to 5 packets. So there is no need to resend third, fourth and fifth packet again. They are buffered in the receiver side. Multi-access. When host on the shared link tries to transfer the data, it has a high probability of collision. Data link layer provides mechanisms such as SysMA CD to equip capability of accessing a shared media among multiple systems. Protocols that listen for a carrier and act accordingly are called carrier sense protocols. Carrier sensing allows the station to detect whether the medium is currently being used. Schemes that use a carrier sense circuits are classed together as carrier sense multiple access or SysMA schemes. These are two variants of SysMA, SysMA CD and SysMA CA. The simplest SysMA scheme is for a station to sense the medium, sending packets immediately if the medium is idle. If the station waits for the medium to become idle, it is called persistent, otherwise it is called non-persistent. Persistent. When a station has the data to send, it first listens to the channel to check if anyone else is transmitting data or not. If it senses the channel is idle, station starts transmitting the data. If it senses the channel is busy, it waits until the channel is idle. When a station detects a channel is idle, it transmits its frames with probability p. This protocol is called p-persistent SysMA. The protocol applies to slotted channels when a station finds the channel idle. If it transmits the frame with probability 1, that this protocol is known as 1 persistent. 1 persistent protocol is the most aggressive protocol. Non-persistent. Non-persistent SysMA is less aggressive compared to p-persistent protocol. In this protocol, before sending the data, the station senses the channel, and if the channel is idle, it starts transmitting the data. But if the channel is busy, the station does not continuously send it, but instead of that it waits for a random amount of time and repeats the algorithm. Here the algorithm leads to better channel utilization but also results in longer delay compared to 1 persistent. SysMA CD. Carrier sense multiple access and collision detection is a technique for multiple access protocols. If no transmission is taking place at the time, the particular station can transmit. If two stations attempt to transmit simultaneously, this causes a collision which is detected by all participating stations. After a random time interval, the stations that collided attempt to transmit again. If another collision occurs, the time intervals from which the random waiting time is selected are increased step by step. This is known as exponential backoff. Exponential backoff algorithm. Number 1. Adapter gets datagram and creates frame. Number 2. If adapter senses channel idle, that is 9.6 microsecond, it starts to transmit frame. If it senses channel busy, waits until channel idle and then transmits. Number 3. If adapter transmits entire frame without detecting another transmission, the adapter is done with frame. Number 4. If adapter detects another transmission while transmitting, aborts and sends jam signal. Number 5. After aborting, adapter enters exponential backoff. Mth collision, adapter chooses a k at random from open curly bracket 0, 1, 2, 2m-1 close curly bracket. Adapter waits k into 512 bit times, that is a slot, and returns to step 2. Number 6. After 10th retry, random number stops at 1023. After 16th retry, system stops to retry. SISMA CA. SISMA CA is carrier sense multiple access and collision avoidance. In this multiple access protocol, station senses the medium before transmitting the frame. This protocol has been developed to improve the performance of SISMA. SISMA CA is used in 802.11 based wireless LANs. In wireless LANs, it is not possible to listen to a medium while transmitting, so collision detection is not possible. In SISMA CA, when the station detects collision, it waits for the random amount of time. Then before transmitting the packet, it listens to the medium. If station senses the medium idle, it starts transmitting the packet. If it detects the medium busy, it waits for the channel to become idle. Ethernet standard and its various frame formats. Ethernet standard. Ethernet is a family of computer network technologies commonly used in local area networks or LANs and metropolitan area networks or MANs. It was commercially introduced in 1980 and first standardized in 1983 EEE 802.3. It has since been refined to support higher bit rates and longer link distances. Ethernet has largely replaced the wired LAN technologies such as token ring, FDDI, and RCnet. The 10-base-PHY Ethernet uses coaxial cable as a shared medium, while the newer Ethernet variants use twisted pair and fiber optic links in conjunction with hubs or switches. Ethernet data transfer rates have been increased from the original 2.94 megabits per second to the latest 100 gigabits per second, with 400 gigabit per second expected by late 2017. The Ethernet standards comprise several wiring and signaling variants of the OSI physical layer in the use with Ethernet. Systems communicating over Ethernet divide a stream of data into shorter pieces called frames. Each frame contains source and destination addresses and error checking data so that damaged frames can be detected and discarded. As per the OSI model, Ethernet provides services up to and including the data link layer. Ethernet has retained a good degree of backward compatibility and has the features such as the 48-bit MAC address and Ethernet frame format have influenced other networking protocols. The primary alternative for some uses of contemporary LANs is Wi-Fi, a wireless protocol standard as IEEE 802.11. In February 1980, the Institute of Electrical and Electronics Engineers, that is IEEE, started Project 802 to standardize local area networks, that is LAN. The DIX group with Gary Robinson from DEC, Phil Ast from Intel, and Bob Prentice from Xerox submitted the so-called Blue Book SISMA CD specification as a candidate for the LAN specification. Various Ethernet frame formats. A data packet on an Ethernet link is called an Ethernet packet, which transports an Ethernet frame as its payload. An Ethernet frame is preceded by a preamble and start frame delimiter (SFD), which are both part of the Ethernet packet at the physical layer. Each Ethernet frame starts with the Ethernet header, which contains destination and source MAC addresses as its first two fields. The middle section of the frame is payload data, including any headers for other protocols, for example Internet Protocol, carried in the frame. The frame ends with a frame check sequence or FCS, which is a 32-bit cyclic redundancy check used to detect any in-transit corruption of data. Ethernet frame structure. A data packet on the wire and the frame as its payload consists of binary data. Data on Ethernet is transmitted with the most significant octet or byte first. Within each octet, however, the least significant bit is transmitted first, except for the frame check sequence or FCS. The internal structure of an Ethernet frame is specified in IEEE 802.3 on 2012. The table below shows the complete Ethernet frame as transmitted for the payload size up to the MTU of 1500 octets. Jumbo frames are large frames supported by some implementations of gigabit Ethernet and other higher speed variants of Ethernet support. 802.3 Ethernet packet and frame structure. Preamble and start frame delimiter. An Ethernet frame starts following a 7-octet preamble and 1-octet start frame delimiter or SFD, both of which are part of the Ethernet packet enveloping the frame. The preamble of an Ethernet packet consists of a 56-bit, a 7-byte pattern of alternating 1 and 0 bits, allowing devices on the network to easily synchronize their receiver clocks, which is followed by the SFD to mark a new incoming frame. For fast Ethernet variants transmitting signal bits instead of larger symbols, the on-the-wire bit pattern for the preamble together with the SFD portion of the frame is 10101010, 10101010, 10101010, 10101010, 10101010, 10101010, 10101010, 10101011. Since octets are transmitted least significant bit first, the corresponding hexadecimal representation is 0x55, 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 0xd5. The SFD is 8-bit or 1-byte value marking the end of the preamble, which is the first field of an Ethernet packet and indicating the beginning of the Ethernet frame. The SFD is designed to break the bit pattern of the preamble and signal the start of the actual frame. The SFD is immediately followed by the destination MAC address, which is the first field in an Ethernet frame. SFD has the value of 171, that is 10101011 in binary notation, which is transmitted with least significant bit first as 213. Header. The header features destination and source MAC addresses, that is each 6 octets in length, the ether type field and optionally a IEEE 802.1q tag. The ether type field is 2 octets long and it can be used for two different purposes. Values of 1500 and below mean that it is used to indicate the size of the payload in octets, while values of 1536 and above indicate that it is used as an ether type to indicate which protocol is encapsulated in the payload of the frame. Either type is the length of the frame is determined by the location of the interpacket gap and valid frame check sequence or FCS. Payload. The minimum payload is 42 octets when an 802.1 queue tag is present and 46 octets when absent. The maximum payload is 1500 octets. Non-standard jumbo frames allow for larger maximum payload size. Frame check sequence. The frame check sequence or FCS is a 4-octet cyclic redundancy check or CRC that allows detection of corrupted data within the entire frame as received on the receiver side. The FCS value is computed as a function of the protected map frame fields, source and destination address, length or type field, MAC client data and padding, that is all fields except the FCS. Running the CRC algorithm over the received frame data including the CRC code will always result in a 0 value for error-free received data, because the CRC is a remainder of the data divided by the polynomial. The technique of false negatives is in which data with trailing zeros will also result in the same zero remainder. To avoid this, the FCS is complemented or reversed for each bit by the sender before it is attached to the end of the payload data. CRC algorithm result will always be a magic number or CRC32 residue of 0xC704DD7B when data has been received correctly. This allows for receiving a frame and validating the FCS without knowing where the FCS field actually starts. End of frame. The end of a frame is usually indicated by the end of data stream at the physical layer or by loss of the carrier signal. An example is 10 base T. Use the loss of carrier detects at the end of the transmitted frame by receiving station. Some physical layers use an explicit end of data or end of stream symbol or sequence to avoid ambiguity. An example is Gigabit Ethernet that uses special symbols of its 8B by 10B encoding scheme which are transmitted before and after a frame is transmitted. Interpacket gap. Interpacket gap is idle time between packets. After a packet has been sent, transmitters are required to transmit a minimum of 96 bits or 12 octets of idle line state before transmitting the next packet. Ethernet frame types. There are several types of Ethernet frames. Ethernet 2 frame or Ethernet version 2 or DIX frame is the most common type in use today, as it is often used directly by the Internet Protocol. Novel Law IEEE 802.3 Non-Standard Variation Frame. IEEE 802.2 Logical Link Control or LLC frame. IEEE 802.2 Subnetwork Access Protocol or SNAP frame. The different frame types have different formats and MTU values, but they are used on the same physical medium. The frame types are basically differentiated based on the Ethernet type and payload start. Following table gives details of Ethernet frame differentiation. Ethernet frame differentiation table. In addition, all 4 Ethernet frames types may optionally contain an IEEE 802.1 Q tag to identify what VLAN it belongs to and its priority or quality of service. This encapsulation is defined in the IEEE 802.3 AC specification and increases the maximum frame by 4 octets. Ethernet 2. Ethernet 2 framing is also known as DIX Ethernet, named after DEC, Intel and Xerox, the major participants in its design, and it defines the 2-octet ether type field in an Ethernet frame. This frame preceded by destination and source MAC addresses that identifies an upper layer protocol encapsulating the frame data. For example, an ether type value of 0x0800 signals that the frame contains an IPv4 datagram. Likewise, an ether type of 0x0806 indicates an ARP frame. 0x8100 indicates an IEEE 802.1q frame, and 86DD indicates an IPv6 frame. The development of IEEE standard went through a formal IEEE standardization process. This process changed the ether type field to a data length field in a new 802.3 standard. Since the recipient still needs to know how to interpret the frame, the standard required an IEEE 802.2 header to follow the length and specify the type. Many years later, the 802.3x on 1997 standard, the later versions of the 802.3 standard approved of both types of framing. In practice, both formats are in wide use with original Ethernet framing in Ethernet local area networks due to its simplicity and lower overhead. Novel RAW IEEE 802.3. Novell's RAW 802.3 frame format was based on early IEEE 802.3 work. Novell used this as a starting point to create the first implementation of its own IPX network protocol over Ethernet. They did not use any LLC header but started the IPX packet directly after the length field. This does not conform to the IEEE 802.3 standard, but since IPX always has FF as the first two octets, this usually coexists on the wire with other Ethernet implementations, with the notable exception of some early forms of DECnet which got confused by this. Novell NetWare used this frame type by default until the mid-90s, and since NetWare was then very widespread, while IP was not, at some point in the most of the world's Ethernet traffic ran over RAW 802.3 carrying IPX. Since NetWare 4.10, NetWare now defaults to IEEE 802.2 with LLC, that is NetWare Frame Type Ethernet 802.2 when using IPX. IEEE 802.2 LLC. The protocols which are designed for the OSI stack operate directly on the top of IEEE 802.2 LLC encapsulation. It provides both connection-oriented and connection-less network services. IEEE 802.2 LLC encapsulation is not in widespread use on common networks, with the exception of large corporate NetWare installations that have not yet migrated to NetWare over IP. In the past, many corporate networks used IEEE 802.2 to support transparent translating bridges between Ethernet and token ring or FDDI networks. An Internet standard used for encapsulating IPv4 traffic in IEEE 802.2 LLC, SAP or SNAP frames. It is almost never implemented on Ethernet, although it is used on FDDI token ring IEEE 802.11 and other IEEE 802 LANs. IP traffic cannot be encapsulated in IEEE 802.2 LLC frames without SNAP because although there is a LLC SAP protocol type for IP, there is no such type for ARP, which is required for operation of any medium to large network. IEEE 802.2 SNAP. The LLC header includes two additional 8-bit address fields called Service Access Points or SAPs in OSI technology. If the SNAP service is requested, then the both source and destination SAP are set to the value 0xAA. The SNAP header allows ether type values to be used with all IEEE 802 protocols as well as supporting private protocol ID spaces. In IEEE 802.3x on 1997, the IEEE Ethernet standard was changed to explicitly allow the use of the 16-bit field after the MAC addresses to be used as a length field or a type field. Frame relay. Frame relay is a standardized wide area network technology that specifies the physical and logical link layers of digital telecommunications channels using a packet switching methodology. Network providers commonly implement frame relay for vice versa, that is VOFR, and data as an encapsulation technique used between local area networks, that is LANs, over a wide area network or WAN. Each end user gets a private line or leased line to a frame relay node. The frame relay network handles the transmission over frequently changing path transparent to all end user extensively used WAN protocols. It is less expensive than leased lines, and that is one reason for its popularity. The extreme simplicity of configuring user equipment in a frame relay network offers another reason for frame relay's popularity. With the advent of Ethernet over fiber optics, MPLS, VPN, and dedicated broadband services such as cable modem and DSL, the end may loom for the frame relay protocol and encapsulation. However, many rural areas remain lacking DSL and cable modem services. In such cases, the least expensive type of non-dial-up connection remains a 64 kilobit per second frame relay line. Thus, a retail chain, for instance, may use frame relay for connecting rural stores into their corporate WAN. Frame relay provide a telecommunication service for cost-efficient data transmission for intermittent traffic between local area networks or LANs and between endpoints in a wide area network or WAN. Frame relay puts data in variable size units called frames and leaves any unnecessary error correction such as a retransmission of data up to the endpoints. This speeds up overall data transmission. For most services, the network provides a permanent virtual circuit, that is PVC, which means that the customer sees a continuous dedicated connection without having to pay for a full-time leased line. While the service provider figures out the route, each frame travels to its destination and can charge based on usage. Frame relay WAN transmission, data terminal equipment or DTE, and data circuit terminating equipment or DCE are required. DTEs are typically located on the customer's premises and can encompass terminals, routers, bridges, and personal computers. DCEs are managed by the carriers and provide switching and associated services. Frame relay has its technical base in the older X.25 packet switching technology designed for transmitting data on analog voice lines. Unlike X.25, whose designers expected analog signals with a relatively high chance of transmission errors, frame relay is a fast packet switching technology operating over links with a low chance of transmission errors, usually practically lossless like PDH, which means that the protocol does not attempt to correct errors. When a frame relay network detects an error in a frame, it simply drops that frame. The endpoints have the responsibility for detecting and retransmitting dropped frames. Protocol Data Unit. Each frame relay protocol data unit or PDU consists of the following fields. Flag field. The flag is used to perform high-level data link synchronization, which indicates the beginning and end of the frame with the unique pattern 01111110 to ensure that the 01111110 pattern does not appear somewhere inside the frame. Bit stuffing and destuffing procedures are used. Address field. Each address field may occupy either octet 223, octet 224, or octet 225, depending on the range of the address in use. A 2-octet address field comprises the EA equals to address field extension bits and the C by R equals to command or response bit. DLCI, Data Link Connection Identifier bits. The DLCI serves to identify the virtual connection so that the receiving end knows which information connection a frame belongs to. Note that this DLCI has only local significance. A single physical channel can multiplex several different virtual connections. FECN, BECN, DE bits. These bits report congestion. FECN equals to forward explicit congestion notification bit. BECN equals to backward explicit congestion notification bit. DE equals to discard eligibility bit. Information field. A system parameter defines the maximum number of data bytes that a host can pick into a frame. Hosts may negotiate the actual maximum frame length at call setup time. The standard specifies the maximum information field size that is supportable by any network as at least 262 octets. Since end-to-end protocols typically operate on the basis of larger information units, Flame Relay recommends that the network support the maximum value of at least 1600 octets in order to avoid the need for segmentation and reassembling by end users. Frame check sequence, that is FCS field. Since one cannot completely ignore the bit error rate of the medium, each switching node needs to implement error detection to avoid wasting bandwidth due to the transmission of errored frames. The error detection mechanism used in Flame Relay uses the cyclic redundancy check or CRC as its basis. Congestion control. The Flame Relay network uses a simplified protocol at each switching node. It achieves simplicity by omitting link-by-link flow control. As a result, the offered load has largely determined the performance of Flame Relay networks. When offered load is high due to the bursts in some services, temporary overload at some Flame Relay nodes cause a collapse in network throughput. Therefore, Flame Relay networks require some effective mechanisms to control the congestion. Congestion control in Flame Relay networks includes the following elements. Admission control. This provides the principal mechanism used in Flame Relay to ensure the guarantee of resource requirement once accepted. It also serves generally to achieve high network performance. The traffic descriptor consists of a set of parameters communicated to the switching nodes at call setup time or at service subscription time, and which characterizes the connection's statistical properties. The traffic descriptor consists of three elements. Committed information rate or CIR, the average rate in bits per second at which the network guarantees to transfer information units over a measurement interval T. This T interval is defined as T equals to BC by CIR. Committed burst size or BC, the maximum number of information units transmittable during the interval T. Excess burst size or BE, the maximum number of uncommitted information units in bits that the network will attempt to carry during the interval. Hardware address or physical addresses. The hardware address, also known as the Ethernet or physical or MAC address, is a 12-byte hexadecimal number that is unique to the Ethernet card on your machine. It will often be displayed in one of the following formats. 08:00:BC:31:DC. 08-00-BC-31-DC. Sometimes leading zeros are omitted. For example, 08-00-BC-31-DC and 8-0-2B-BC-31-DC refer to the same hardware address. To determine your computer's hardware address, on a computer running Windows 7, press the Start button, type CMD, then press Enter to start up a command shell. Type ipconfig/all. The hardware address will be listed under physical address. On Mac OS X, select System Preferences from the Apple menu. Select Network. Select your Ethernet adapter from the menu on the left. Click the Advanced button. Click the Hardware tab. The hardware MAC address will be shown below. On Linux, run sbin/ifconfig-a. The hardware address for each Ethernet interface will be listed in the output after the string HWADDR. On Solaris, become root. Run /usr/sbin/ifconfig-a. The hardware address for each Ethernet interface will be listed in the output after the string ether. A MAC address is given to a network adapter when it is manufactured. It is hardwired or hard-coded onto your computer's network interface card or NIC and is unique to it. The ARP or Address Resolution Protocol translates an IP address into a MAC address. The ARP is like a passport that takes data from an IP address through an actual piece of computer hardware. Hardware and software working together, IP addresses and MAC addresses working together, so the MAC address is sometimes referred to as a networking hardware address, the burned-in address or BIA, or the physical address. An example of a MAC address for an Ethernet NIC: 00:0A:95:9D:68:16. MAC address itself doesn't look anything like an IP address. The MAC address is a string of usually 6 sets of 2 digits or characters separated by colons. Networks and MAC addresses. All devices on the same network subnet have different MAC addresses. MAC addresses are very useful in diagnosing network issues, such as problems with IP addresses. MAC addresses are useful for network diagnosis because they never change, as opposed to a dynamic IP address which can change from time to time. For a network administrator, that makes a MAC address a more reliable way to identify senders and receivers of data on the network. On wireless networks, a process called MAC filtering is a security measure to prevent unwanted network access by hackers and intruders. In MAC address filtering, the router is configured to accept traffic only from specific MAC addresses. This way, computers whose MAC addresses are approved will be able to communicate through the network, even if they were given a new IP address by DHCP. A hacker who's hijacked a network IP address will be blocked because their MAC address will not be on the approved list and will be filtered out. PPP authentication protocol like PAP and CHAP. For link security, PPP provides 2 optional authentication protocols. These are used during initial link setup by the Link Control Protocol or LCP to deny PPP connections to unauthorized devices. The 2 authentication protocols are the Password Authentication Protocol or PAP and Challenge Handshake Authentication Protocol, that is CHAP. PAP and CHAP are control protocols. However, since they have a very different purpose than LCP and many of the other control protocols, they use a distinct set of frames with their own unique set of code values. PAP uses 3 different control frame types and CHAP uses 4. Password Authentication Protocol or PAP. Password Authentication Protocol or PAP is an authentication protocol that uses a password. PAP is used by point-to-point protocol to validate users before allowing them access to server resources. Almost all network operating system remote servers support PAP. PAP transmits unencrypted ASCII passwords over the network and is therefore considered insecure. It is used as a last resort when the remote server does not support a stronger authentication protocol like CHAP or EAP. The latter is actually a framework. Password-based authentication is the protocol where 2 entities share a password in advance and use the password as the basis of authentication. Password authentication schemes can be categorized into 2 types: weak password authentication schemes and strong password authentication schemes. When compared to strong password schemes, weak password schemes tend to have lighter computational overhead, the designs are simpler, and implementation is easier, making them especially suitable for some constrained environments. The working cycle of PAP is given below. Number 1. Client sends username and password. Number 2. Server sends authentication-ACK if credentials are OK or authentication-NAK otherwise. PAP packet. PAP packets description are shown in the following table. Description 1 byte, 1 byte, 2 bytes, 1 byte, variable, 1 byte, variable. Authentication-request, code equals to 1, ID, length, username, password length, password. Authentication-ACK, code equals to 2, ID, length, message. Authentication-NAK, 3, ID, length, message. PAP packet embedded in a PPP frame. The protocol field has a value of C023 in hexadecimal. Flag, address, control, protocol C023 in hex, payload, table above, FCS, flag. Challenge Handshake Authentication Protocol or CHAP. Challenge Handshake Authentication Protocol or CHAP authenticates a user or network host to authenticating entity. For example, that entity may be an internet service provider. CHAP is specified in RFC 1994. CHAP provides protection against replay attacks by the peer through the use of an incrementally changing identifier and of a variable change value. CHAP requires that both the client and server know the plain text of the secret, although it is not sent over the network. Thus, CHAP provides better security as compared to Password Authentication Protocol or PAP, which is vulnerable for both these reasons. The MS-CHAP variant does not require either peer to know the plain text and does not transmit it, but has been broken. CHAP is an authentication scheme used by point-to-point protocol or PPP servers to validate the identity of remote clients. CHAP periodically verifies the identity of the client by using a three-way handshake. This happens at the time of establishing the initial link, that is LCP, and may happen again at any time afterwards. The verification is based on a shared secret, that is such as the client user's password. After the completion of the link establishment phase, the authenticator sends a challenge message to the peer. The peer responds with a value calculated using a one-way hash function on the challenge and the secret combined. The authenticator checks the response against its own calculation of the expected hash value. If the value matches, the authenticator acknowledges the authentication, otherwise it should terminate the connection. At random intervals, the authenticator sends a new challenge to the peer and repeats step 1 through 3. CHAP packets are shown in the following table. The ID chosen for the random challenge is also used in the corresponding response, success, and failure packets. The new challenge with a new ID must be different from the last challenge with another ID. If the success or failure is lost, the same response can be sent again, and it triggers the same success or failure indication. For MD5 as hash, the response value is the concatenation of ID, secret, and challenge. CHAP versus PAP. PAP works basically the same way as the normal login procedure. The client authenticates itself by sending a username and an optionally encrypted password to the server, which the server compares to its secrets database. This technique is vulnerable to eavesdroppers who may try to obtain the password by listening in on the serial line and to repeated trial and error attacks. CHAP does not have these deficiencies. With CHAP, the authenticator, that is the server, sends a randomly generated challenge string to the ring along with its host name. The client uses the host name to look up the appropriate secret, combines it with the challenge, and encrypts the string using a one-way hashing function. The result is returned to the server along with the client's hostname. The server now performs the same computation and acknowledges the client if it arrives at the same result. Another feature of CHAP is that it does not only require the client to authenticate itself at startup time, but sends challenges at regular intervals to make sure the client hasn't been replaced by an intruder, for instance, by just switching phone lines. PPPD keeps the secret keys for CHAP and PAP in two separate files called /etc/ppp/chap-secrets and pap-secrets, respectively. By entering a remote host in one or the other file, we have a fine control over whether CHAP or PAP is used to authenticate ourselves with our peer and vice versa. Point-to-point protocol. In computer networking, point-to-point protocol or PPP is a data link protocol used to establish a direct connection between two nodes. It can provide connection authentication, transmission encryption using ECP, RFC 1968, and compression. PPP is used over many types of physical networks including serial cable, phone line, trunk line, cellular telephone, specialized radio links, and fiber optic links such as SONET. PPP is also used over Internet access connections. Internet service providers or ISPs have used PPP for customers' dial-up access to the Internet. Since IP packets cannot be transmitted over modem line on their own without some data link protocol, two derivatives of PPP, point-to-point protocol over Ethernet or PPoE, and point-to-point protocol over ATM or PPPoA, are used most commonly by Internet service providers or ISPs to establish a digital subscriber line or DSL Internet service connection with customers. PPP is commonly used as a data link layer protocol for connection. PPP is a full duplex protocol that can be used on various physical media, including twisted pair or fiber optic lines or satellite transmission. It uses a variation of high-speed data link control or HDLC for packet encapsulation. PPP is usually preferred over the earlier de facto standard serial line Internet protocol or SLIP because it can handle synchronous as well as asynchronous communication. PPP can share a line with other users and it has error detection that slip black. Over synchronous and asynchronous circuits, where it has largely superseded the older serial line Internet protocol or SLIP and telephone company mandated standards such as Link Access Protocol, Balanced or LAPB in the X.25 protocol suite. The only requirement for PPP is that the circuit provided be duplex. PPP was designed to work with numerous network layer protocols including Internet Protocol or IP, TRIL, Novell's Internetwork Packet Exchange or IPX, NBF, DECnet, and AppleTalk. PPP permits multiple network layer protocols to operate on the same communication link. For every network layer protocol used, a separate network control protocol or NCP is provided in order to encapsulate and negotiate options for the multiple network layer protocols. It negotiates network layer information, for example, network address or compression options after the connection has been established. For example, Internet Protocol or IP uses the IP Control Protocol that is IPCP and Internetwork Packet Exchange that is IPX uses the Novell IPX Control Protocol that is IPX/SPX. NCPs include fields containing standardized codes to indicate the network layer protocol type that the PPP connection encapsulates. The following NCPs may be used with PPP. The Internet Protocol Control Protocol that is IPCP for the Internet Protocol, protocol code number 0x8021, RFC 1332. The OSI Network Layer Control Protocol or OSINLCP For the various OSI network layer protocols, protocol code number 0x8023 RFC 1377. The Apple Talk Control Protocol or ATCP for Apple Talk, protocol code number 0x8029 RFC 1378. The Inter-Network Packet Exchange Control Protocol or IPXCP for the Internet Packet Exchange, protocol code number 0x802B RFC 1552. The DEC Net Phase 4 Control Protocol or DNCP for DNA Phase 4 Routing Protocol, that is DEC Net Phase 4, protocol code number 0x8027 RFC 1762. The NetBIOS Frames Control Protocol, that is NBFCP for NetBIOS Frames Protocol or NetBEUI as it was called before that, protocol code number 0x803F RFC 2097. The IPv6 Control Protocol or IPv6CP for IPv6, protocol code number 0x8057 RFC 5072. PPP may include the following LCP options. Authentication. Peer routers exchange authentication messages. Two authentication choices are Password Authentication Protocol or PAP and Challenge Handshake Authentication Protocol, that is CHAP. Compression increases the effective throughput on PPP connections by reducing the amount of data in the frame that must travel across the link. The protocol decompresses the frame at its destination. Error detection identifies fault conditions. The quality and magic number options help ensure a reliable, loop-free data link. The magic number field helps in detecting links that are in a looped back condition. Until the magic number configuration option has been successfully negotiated, the magic number must be transmitted as 0. Magic numbers are generated randomly at each end of the connection. Multi-link provides load balancing several interfaces used by PPP through multi-link PPP. Structure of PPP frame. PPP frames are variants of HDLC frames. If both peers agree to address field and control field compression during LCP, then those fields are omitted. Likewise, if both peers agree to protocol field compression, then the 0x00 byte can be omitted. The protocol field indicates the type of payload packet, that is 0xC021 for LCP, 0x80XY for various NCPs, 0x0021 for IP, 0x0029 Apple Talk, 0x002B for IPX, 0x003D for multi-link, 0x003F for NetBIOS, 0x00FD for MPPC and MPPE, etc. PPP is limited and cannot contain general layer 3 data unlike Ether type. The information field contains the PPP payload. It has a variable length with a negotiated maximum called the maximum transmission unit. By default, the maximum is 1500 octets. It might be padded on transmission. If the information for a particular protocol can be padded, that protocol must allow information to be distinguished from padding. STP, the Spanning Tree Protocol or STP, is a network protocol that builds a logical loop-free topology for Ethernet network. The basic function of STP is to prevent bridge loops and the broadcast radiation that results from them, where two bridges are used to interconnect the same two computer network segments. Spanning Tree Protocol allows the bridges to exchange information, so that only one of them will handle a given message that is being sent between two computers within the network. The Spanning Tree Protocol prevents the condition known as a bridge loop. If too many computers try to send at the same time, the overall performance of the network can be affected, even to the point of bringing all traffic to a near halt. To make this possibility, the local area network can be divided into two or more network segments with a device called a bridge connecting any two segments. Each message, called a frame, goes through the bridge before being sent to the intended destination. The bridge determines whether the message destination is within the same segment as the senders or for the other segment, and forwards it accordingly. A bridge does nothing more than look at the destination address and based on its understanding of the two segments, which computers are on which segments, forwards it on the right path, which means to the correct outgoing port. The benefit of network segmentation and the bridge is that the amount of competition for use of the network path is reduced by half. Open parenthesis, assuming each segment has the same number of computers, close parenthesis, and the possibility of the network coming to a halt is significantly reduced. Each bridge learns which computers are on which segment by sending any first-time message to both segments. This is known as flooding, and then noticing and recording the segment from which a computer replied to the message. Gradually, the bridge builds a picture for itself of which computers are in which segments. When subsequent messages are sent, the bridge can use its table to determine which segment to forward it to. The approach of allowing the bridge to learn the network through experience is known as transparent bridging, open parenthesis, meaning that the bridging does not require setup by an administrator, closed parenthesis. In order to build into a network, it is typically to add a second bridge between two segments as a backup in case the primary bridge fails. Both bridges need to continually understand the topography of the network, even though only one is actually forwarding messages, and both bridges need to have some way to understand which bridge is the primary one. To do this, they have a separate path connection just between the bridges in which they exchange information, using Bridge Protocol Data Units (BPDUs). The program in each bridge that allows it to determine how to use the protocol is known as the spanning tree algorithm. The algorithm is specially constructed to avoid bridge loops, that is multiple paths linking one segment to another, resulting in an infinite loop situation. The algorithm is responsible for a bridge using only the most efficient path when faced with multiple paths. If the best path fails, the algorithm recalculates the network and finds the next best route. Spanning tree algorithm determines the network, which computer hosts are in which segment, and this data is exchanged using Bridge Protocol Data Units, that is BPDUs. It is broken down into two steps. Step 1. The algorithm determines the best message a bridge can send by evaluating the configuration messages it has received and choosing the best option. Step 2. Once it selects the top message for a particular bridge to send, it compares its choice with possible configuration messages from the non-root connections it has. If the best option from step 1 isn't better than what it receives from the non-root connections, it will prune that port. Bridge Protocol Data Units. The above rules describe one way of determining what spanning tree will be computed by the algorithm require knowledge of the entire network. The bridges have to determine the root bridge and compute the port roles, that is root, designated or blocked, with only the information that they have. To ensure that each bridge has enough information, the bridges use special data frames called Bridge Protocol Data Units or BPDUs to exchange information about bridge IDs and route path costs. A bridge sends a BPDU frame using the unique MAC address of the port itself as a source address and a destination address of the STP multicast address 01:80:C2:00:00:00. There are two types of BPDUs in the original STP specification, that is the Rapid Spanning Tree or RSTP extension uses a specific RSTP BPDU. Configuration BPDU or CBPDU used for spanning tree computation. Topology Change Notification TCN BPDU used to announce changes in the network topology. BPDUs are exchanged regularly every 2 seconds by default and enable switches to keep track of network changes and to start and stop forwarding at ports as required. When a device is first attached to a switch port, it will not immediately start to forward data. It will instead go through a number of states while it processes BPDUs and determines the topology of the network. Topology change notification, that is TCN, BPDUs are used to inform other switches of port changes. TCNs are injected into the network by a known root switch and propagated to the root. Upon receipt of the TCN, the root switch will set a topology change flag in its normal BPDUs. This flag is propagated to all other switches to instruct them to rapidly age out their forwarding table entries. STP switch port states. Blocking. A port that would cause a switching loop if it were active. BPDU data is still received in blocking state, prevents the use of looped paths. Listening. The switch processes BPDUs and awaits possible new information that will cause it to return to a blocking state. It does not populate the MAC address table and frames. Learning. While the port does not yet forward frames, it does learn source addresses from frames received and adds them to the filtering database, that is switching database. It populates the MAC address table but does not forward frames. Forwarding. A port receiving and sending data, normal operation. STP still monitors incoming BPDUs that would indicate it should return to a blocking state to prevent a loop. Disabled. Not strictly part of STP, a network administrator can manually disable a port. To prevent the delay when connecting hosts to a switch and during some topology changes, Rapid STP was developed, which allows a switch port to rapidly transition into the forwarding state during these situations. Bridge Protocol Data Unit Fields. IEEE 802.1d and IEEE 802.1aq BPDUs have the following format. Number 1. Protocol ID 2 bytes, that is 0x0000 IEEE 802.1d. Number 2. Version ID 1 byte, that is 0x00 config and TCN / 0x02 RST / 0x03 MSTP / 0x04 SPT BPDU. Number 3. BPDU type 1 byte, that is 0x00 config BPDU, 0x80 TCN BPDU, 0x02 RST BPDU. Number 4. Flag 1 byte. Bits. Usage 1. 0 or 1 for topology change. 2. 0 or unused or 1 for proposal in RST / MST / SPT BPDU. 3 to 4. 00 or unused or 01 for port role alternate or backup in RST or MST or SPT BPDU. 10 for port role root in RST or MST or SPT BPDU. 11 for port role designated in RST or MST or SPT BPDU. 5. 0 or unused or 1 for learning in RST or MST or SPT BPDU. 6. 0 or unused or 1 for forwarding in RST or MST or SPT BPDU. 7. 0 or unused or 1 for agreement in RST or MST or SPT BPDU. 8. 0 or 1 for topology change acknowledgement. Number 5. Root ID 8 bytes open bracket CIST root ID in MST or SPT BPDU closed bracket. Bits. Usage 1 to 4. Root bridge priority 5 to 16. Root bridge system ID extension 17 to 64. Root bridge MAC address. Number 6. Root path cost 4 bytes, that is CIST external path cost in MST or SPT BPDU. Number 7. Bridge ID 8 bytes, that is CIST regional root ID in MST or SPT BPDU. Bits. Usage 1 to 4. Bridge priority 5 to 16. Bridge system ID extension 17 to 64. Bridge MAC address. Number 8. Port ID 2 bytes. Number 9. Message age 2 bytes in 1 bar 256 seconds. Number 10. Maximum age 2 bytes in 1 bar 256 seconds. Number 11. Hello time 2 bytes in 1 bar 256 seconds. Number 12. Forward delay 2 bytes in 1 bar 256 seconds. Number 13. Version 1 length 1 byte, that is 0x00, no version 1 protocol info present, RST, MST, SPT, BPDU only. Number 14. Version 3 length 2 bytes, that is MST, SPT, BPDU only. The TCN BPDU includes fields 1 to 3 only. Protocol operations. A local area network or LAN can be depicted as a graph whose nodes are bridges and LAN segments or cables, and whose edges are the interface connecting the bridges to the segments. To break loops in the LAN while maintaining access to all LAN segments, the bridges collectively compute a spanning tree. The spanning tree that the bridges compute using the spanning tree protocol can be determined using the following rules. The example network will be used to illustrate the rules are summarized below. An example network, the numbered boxes represent bridges, that is the number represents the bridge ID. The lettered clouds represent network segments. The smallest bridge ID is 3. Therefore, bridge 3 is the root bridge. Assuming that the cost of traversing any network segment is 1, the least cost path from bridge 4 to the root bridge goes through the network segment C. Therefore, the root port for bridge 4 is the 1 on network segment C. The least cost path to the root from network segment goes through bridge 92. Therefore, the designated port for network segment E is the port that connects bridge 92 to network segment E. This diagram illustrates all port states as computed by the spanning tree algorithm. Any active port that is not a root port or a designated port is a blocked port. After link failure, the spanning tree algorithm computes and spans new least cost tree. The above rules oversimplify the situation slightly because it is possible that there are ties. For example, the root bridge may have 2 or more ports on the same LAN segment. 2 or more ports on a single bridge are attached to least cost path to the root, or 2 or more bridges on the same network segment have equal least cost path to the root. To break such ties, breaking ties for root port. When multiple paths from a bridge are least cost path, the chosen path uses the neighbor bridge with the lower bridge ID. The root port is thus the one connecting to the bridge with the lowest bridge ID. Breaking ties for designated port. When the root bridge has more than one port on a single LAN segment, the bridge ID is effectively tied. The designated port then becomes the port on that LAN segment with the lowest port ID. It's put into forwarding mode while all other ports on the root bridge in same LAN segment become non-designated ports and are become blocking mode. When more than one bridge on a segment leads to a least cost path to the root, the bridge with the lower bridge ID is used to forward messages to the root. The port attaching that bridge to the network segment is the designated port for the segment. The final tie breaker. In some cases, there may still be a tie. When the root bridge has multiple active ports on the same LAN segment with equally low root path, costs, and bridge IDs. Multiple bridges are connected by multiple cables and multiple ports. Single bridge may have multiple candidates for its root port. In these cases, candidates for the root port have already received BPDUs offering equally low, that is the best, root path cost and equally low, that is the best, bridge IDs, and the final tiebreaker goes to the port that received the lowest, that is the best, port priority ID or port ID. In summary, the sequence of events to determine the best received BPDU is: lowest root bridge ID determines the root bridge. Lowest cost to the root bridge favors the upstream switch with the least cost to the root. Lowest sender bridge ID serves as a tiebreaker if multiple upstream switches have equal cost to root. Lowest sender port ID serves as a tiebreaker if a switch has multiple non-ether channel links to a single upstream switch where bridge ID equals to priority 4 bits plus locally assigned system ID extension 12 bits plus ID MAC address 48 bits. The default bridge priority is 32768 and port ID equals to priority 4 bits plus ID interface number 12 bits. The default port priority is 128. The spanning tree protocol and algorithm were developed by a committee of the IEEE. Currently, the IEEE is attempting to institute enhancements to the spanning tree algorithm that will reduce network recovery time. The goal is to go from 30 to 60 seconds after a failure or change in link status to less than 10 seconds. The enhancement, called Rapid Reconfiguration of Fast Spanning Tree, that is RSTP, would cut down on data loss and session timeouts when large Ethernet networks recover after a topology change or a device failure. Serial links. Serial communication is the process of sending data one bit at a time, sequentially, over a communication channel or computer bus. This is in contrast to parallel communication, where several bits are sent as a whole on a link with several parallel channels. Serial links offer significant flexibility over parallel buses in terms of the media used. Both fiber channel and gigabit Ethernet standards specify interfaces to fiber optic and copper interfaces. Module-based serial connectors can be used, enabling the user to switch between copper and a variety of fiber types simply by switching the module type on a port. For example, the Gigabit Interface Converter or GBIC module is a removable, hot-swappable unit that allows easy conversion between media simply by changing the module. This module also allows blind mating with the receptacle. It enables the user to easily replace or test defective modules on a board. The user can also switch between copper or fiber after the system has been designed and installed in a system. This is impossible with current parallel backplane technology. Serial links forms are from 2400 bps dial-up modems and their faster cousins to dedicated T3 leased lines. They interconnect two computers and transmit a single bit at a time in each direction. The stream of bits is assembled into bytes and then packet. The speed of a serial line is rated in bits per second, that is BPS. They can be broken into two broad categories, synchronous and asynchronous. Synchronous serial links. Synchronous links use a clock signal by which a clock signal is transmitted along with the data. This can take many forms. A separate signal may carry the clock. In this example, the sender transmits each bit on a rising edge of the clock. The receiver latches the data signal on the trailing edge of the clock. The race conditions between the two are avoided. Every clock cycle, a single bit is transferred. It is also possible to combine the clock and data signals together into one. In this example, every 0 bit is encoded as a full clock cycle, while 1 bits are encoded by skipping a transition in the middle of the cycle. The decoding circuitry is more complex, but fewer wires are required in this scheme. In any event, such serial links are termed synchronous because the data signal is synchronized with a clock signal. Most serial links are synchronous. Low-speed modems and printers form the exception. Typically, one side of the link provides clocking, gives clock, for data traveling in both directions. The other side of the link takes clock. Asynchronous serial links. Asynchronous links lack any form of clock signal. A start bit is used to signal the beginning of the transmission. Once the receiver has seen the start bit, it begins counting bit times according to the pre-configured line speed. Without an explicit clock signal, the receiver risks gradually losing synchronization with the sender. For this reason, almost all asynchronous links transmit only a single byte at a time. The next byte requires a new start bit to resynchronize the sender and receiver. Asynchronous links, since they lack clocking, require the sender and receiver to agree on the bit speed of the link. If they do not agree, for example if the sender transmits at 14.4 kbps but the receiver is configured for 9.6 kbps, gibberish will result, as almost anyone with an external modem has experienced from time to time. Standard HDLC protocols. HDLC, or High Level Data Link Control, is a transmission protocol used at the data link layer, that is layer 2 of the OSI 7-layer model of data communications. The HDLC protocol embeds information in a data frame that allows devices to control data flow and correct errors. HDLC is an ISO standard developed from the Synchronous Data Link Control, or SDLC, standard proposed by IBM in the 1970s. High-level data link control, or HDLC, is a bit-oriented code-transparent synchronous data link layer protocol developed by the International Organization for Standardization, or ISO. The original ISO standards for HDLC are ISO 3309 Frame Structure, ISO 4335 Elements of Procedure, ISO 6159 Unbalanced Classes of Procedure, ISO 6256 Balanced Classes of Procedure. The current standard for HDLC is ISO 13239, which replaces all of those standards. HDLC provides both connection-oriented and connection-less service. HDLC is a bit-oriented protocol that supports both half-duplex and full-duplex communication over point-to-point and multi-point link. For HDLC communications, one station is designated primary and the other secondary. A session can use one of the following connection modes, which determine how the primary and secondary stations interact. Normal unbalanced. The secondary station responds only to the primary station. Asynchronous. The secondary station can initiate a message. Asynchronous balanced. Both stations send and receive over its part of a duplex line. This mode is used for X.25 packet switching networks. The Link Access Procedure Balanced, or LAP-B, and Link Access Procedure D-Channel, or LAP-D, protocols are subsets of HDLC. The following table summarizes the HDLC subsets and its uses. LAPB is a bit-oriented synchronous protocol that provides complete data transparency in a full duplex point-to-point operation. It supports a peer-to-peer link in that neither end of the link plays the role of the permanent master station. HDLC LAPB is a very efficient protocol which requires a minimum of overhead to ensure flow control, error detection, and recovery. If data is flowing in both directions, that is full duplex, the data frames themselves carry all the information required to ensure data integrity. The concept of a frame window is used to send multiple frames before receiving confirmation that the first frame has correctly been received. This means that the data can continue to flow in situations where there may be long turnaround time lags without stopping to wait for an acknowledgement. This kind of situation occurs, for instance, in satellite communication. Types of frames in HDLC. HDLC defines three types of frames. Number 1. Information frames, or I frame. Supervisory frame, or S frame. Number 3. Unnumbered frame, or U frame. Information frames. I frames carry users' data and control information about users' data. I carries user data in the information field. The I frame format is shown in the diagram. The first bit of control field is always 0. That is, the presence of 0 at this place indicates that it is I frame. Bit number 2, 3, and 4 in control field is called N inside bracket S, that specifies the sequence number of the frame. Thus, it specifies the number of the frame that is currently being sent. Since it is a 3-bit field, only 8 sequence numbers are possible: 0, 1, 2, 3, 4, 5, 6, 7, or 000 to 111. Bit number 5 in control field is P bar F, that is pole or final, and is used for these two purposes. It has meaning only when it is set, that is when P bar F equals to 1. It can represent the following two cases. It means pole when frame is sent by a primary station to secondary when address field contains the address of receiver. It means final when frame is sent by secondary to a primary when the address field contains the address of the sender. Bit number 6, 7 and 8 in control field specifies N inside bracket R, that is the sequence number of the frame expected in return in two-way communication. If last frame received was error-free, then N inside bracket R number will be that of the next frame is sequence. If the last frame was not received correctly, the N inside bracket R number will be the number of the damaged frame asking for its retransmission. Supervisory frame. S frame carries control information, primarily data link layer flow and error controls. It does not contain information field. The format of S frame is shown in diagram. The first two bits in the control field of S frame are always 10. Then there is a bit code field that specifies four types of S frame with combination 00, 01, 10, 11 as shown in table. RR. Receive ready, used to acknowledge frames when no iframes are available to piggyback the acknowledgement. REJ. Reject, used by the receiver to send a NAK when error has occurred. RNR. Receive not ready, used for flow control. SREJ. Selective reject, indicates to the transmitter that it should retransmit the frame indicated in the N of R subfield. There is no N of S field in control field of S frame, as S frames do not transmit data. P bar F bit is the fifth bit and serves the same purpose as discussed earlier. Last three bits in control field indicates N of R, that is, they correspond to the ACK or NAK value. Unnumbered frame. U frames are reserved for system management and information carried by them is used for managing the link. U frames are used to exchange session management and control information between the two connected devices. Information field in U frame does not carry user information, rather, it carries system management information. The frame format of U frame is shown in diagram. U frame is identified by the presence of 11 in the first and second bit position in control field. These frames do not contain N of S or N of R in control field. U frame contains two code fields, 1, 2, hit and other 3 bit. These 5 bits can create up to 32 different U frames. P bar F bit in control field has some purpose in V frame as discussed earlier. Protocol structure HDLC, High Level Data Link Control. Flag. The value of the flag is always 0x7e. Address field defines the address of the secondary station which is sending the frame or the destination of the frame sent by the primary station. It contains service access point, that is 6 bits, a command bar response bit to indicate that the frame relates to information frames or iframes being sent from the node or received by the node, and an address extension bit which is usually set to true to indicate that the address is of length 1 byte. When set to false, it indicates an additional byte follows. Extended address. HDLC provides another type of extension to the basic format. The address field may be extended to more than 1 byte by agreement between the involved parties. Control field serves to identify the type of the frame. In addition, it includes sequence numbers, control features, and other tracking according to the frame type. FCS. The frame check sequence or FCS enables a high level of physical error control by allowing the integrity of the transmitted frame data to be checked. Related protocols: LAPB, ISDN, X.25, Frame Relay, SDLC. Switching process. Through the switching process, the router determines the next hop toward the destination address. Switching moves traffic from an input interface to one or more output interfaces. Switching is optimized and has lower latency than routing because it can move packets, frames, or cells from buffer to buffer with simpler determination of the source and destination of the traffic. It saves resources because it does not involve extra lookups. Figure 1 illustrates the basic switching process. Packets are received on the fast Ethernet interface and destined for the FDDI interface. Based on information in the packet header and destination information stored in the routing table, the router determines the destination interface. It looks in the routing table of the protocol to discover the destination interface that services the destination address of the packet. The destination address is stored in tables such as ARP tables for IP or AARP tables for AppleTalk. If there is no entry for the destination, the router will either drop the packet and inform the user if the protocol provides that feature, or discover the destination address by some other address resolution process such as through ARP. Layer 3 IP addressing information mapped to the Layer 2 MAC address for the next hop. Figure 2 illustrates the mapping that occurs to determine the next hop. Basic switching paths. Basic switching paths are described in the following sections: process switching, fast switching, CEF switching, DCEF switching. Process switching. In process switching, the first packet is copied to the system buffer. The router looks up the layer 3 network address in the routing table and initializes the fast switch cache. The frame is rewritten with the destination address and sent to the outgoing interface that services that destination. Subsequent packets for that destination are sent by the same switching path. Fast switching. When packets are fast switched, the first packet is copied to packet memory and the destination network or host is found in the fast switching cache. The frame is rewritten and sent to the outgoing interface that services the destination. Subsequent packets for the same destination use the same switching path. The interface processor computes the CRC. CEF switching. When CEF mode is enabled, the CEF, FIB and urgency tables reside on the RP and the RP performs the express forwarding. We use CEF mode when line cards are not available for CEF switching or when we need to use features not compatible with DCEF switching. DCEF switching. In distributed switching, the switching process occurs on VIP or other interface cards that support switching. When DCEF is enabled, line cards such as VIP line cards or GSR line cards maintain an identical copy of the FIB and urgency tables. The line cards perform the express forwarding between port adapters, relieving the RSP of involvement in the switching operation. DCEF uses an inter-process communication or IPC mechanism to ensure synchronization of FIBs and urgency tables on the RP and line cards. The VIP card installed in this router maintains a copy of the routing cache information needed to forward packets. Because the VIP card has the routing information it needs, it performs the switching locally, making the packets forwarding much faster. Router throughput is increased linearly based on the number of VIP cards installed in the router. Depending on the routing platform faced, availability and default implementations of switching paths varies. Multi-protocol label switching or MPLS distribution protocol. The multi-protocol label switching or MPLS distribution protocol (MPLS) is a high-performance packet forwarding technology that integrates the performance and traffic management capabilities of data link layer, layer 2, switching with the scalability, flexibility, and performance of network layer, that is layer 3 routing. It enables service providers to meet challenges brought about by explosive growth and provides the opportunity to differentiate services without necessitating the sacrifice of existing infrastructure. The MPLS architecture regarding for its flexibility. Point. Data can be transferred over any combination of layer 2 technologies. Point. Support is offered for all layer 3 protocols. Point. Scaling is possible well beyond anything offered in today's networks. Specifically, MPLS can efficiently enable the delivery of IP services over an ATM switched network. Its creation of different routes between a source and a destination on a purely router-based internet backbone. Service providers who use MPLS can save money and increase revenue and productivity. Multi-layer switching. MLS provides high-performance layer 3 switching for routers and switches. MLS switches IP data packets between subnets using advanced application-specific integrated circuit, that is ASIC, switching hardware. Standard routing protocols such as Open Shortest Path First or OSPF, Enhanced Interior Gateway Routing Protocol, or Enhanced IGRP, Routing Information Protocol, or RIP, and Intermediate System to Intermediate System, that is IS to IS, are used for route determination. MLS enables hardware-based layer 3 switching to offload routers from forwarding unicast IP data packets over shared media networking technologies such as Ethernet. The packet forwarding function is moved onto layer 3 switches whenever a partial or complete switched path exists between two hosts. Packets that do not have a partial or complete switched path to reach their destinations still use routers for forwarding packets. MLS also provides traffic statistics as part of its switching function. These statistics are used for identifying traffic characteristics for administration, planning, and troubleshooting. MLS uses Net Flow Data Export or NDE to export the flow statistics. Multicast distributed switching. Multicast distributed switching IP multicast traffic was always switched at the route processor or RP in the route switch processor or RSP based platforms of IP multicast traffic can be distributed switched on RSP based platforms with VIPs. Switching multicast traffic at the RP had the following disadvantages. Point. The load on the RP increased. This affected important route updates and calculations for BGP, among others, and could stall the router if the multicast load was substantial. Point. The net multicast performance was limited to what a single RP could switch. MDS solves these problems by performing distributed switching of multicast packets received at the line cards, open parenthesis, VIPs in the case of RSP and line cards in the case of GSR, close parenthesis. The line card is the interface card that houses the VIPs, open parenthesis, in the case of RSP, close parenthesis, and the GSR line card in the case of GSR. MDS is accomplished using a forwarding data structure called a multicast forwarding information or MFIB, which is a subset of the routing table. A copy of MFIB runs on each line card and is always kept up to date with the MFIB table of the RP. In the case of RSP, packets received on non-VIP IPs are switched by the RP. MDS can work in conjunction with Cisco Express Forwarding or CEF, Unicast Distributed Fast Switching or DFS, or Flow Switching. VLAN routing. Communication between VLANs. Communication between VLANs is accomplished through routing, and the traditional security and filtering functions of the router can be used. iOS software provides network services such as security filtering, quality of service, that is QoS, and accounting on a per VLAN basis. Functionality of IEEE 802.1q support for bridging on those interfaces and the capability to configure and use integrated routing and bridging, that is IRB. The following section describes how bridging communication between IEEE 802.1q VLANs occurs. Relaying function, native VLAN, PVST+, integrated routing and bridging. Relaying function. The relaying function level as displayed in figure below the architectural model described in the IEEE 802.1q standard and presents three types of rules. Ingress rules. Rules relevant to the classification of received frames belonging to a VLAN. Forwarding rules between ports decides to filter or forward the frame. Egress rules. Output of frames from the switch decides if the frame must be sent tagged or untagged. Figure relaying function. Port state information, forwarding process, port state information. Ingress rules, filtering database, egress rules, frame reception, frame transmission. The tagging scheme. Figure shows the tagging scheme proposed by the 802.3 AC standard. Supports the addition of the 4 octets after the source MAC address. Their presence is indicated by a particular value of the ether type field called TPID, which has been fixed to be equal to 0x8100. When a frame has the ether type equal to 0x8100, it carries the tag IEEE 802.1q/802.1p. The tag is stored in the following 2 octets and it contains 3 bits of user priority, 1 bit of canonical format identifier, that is CFI, and 12 bits of VLAN ID, that is VID. The 3 bits of user priority are used by the 802.1p standard. The CFI is used for compatibility reasons between Ethernet type networks and token ring type networks. The VID is the identification of the VLAN, which is basically used by the 802.1q standard. Being on 12 bits, it allows the identification of 4096 VLANs. After the 2 octets of TPID and the 2 octets of the tag control information field, the 2 octets are located after the source address field where there is the TPID. They contain either the MAC length in the case of IEEE 802.3 or the ether type in the case of Ethernet version 2. Figure tagging scheme. The ether type and VLAN ID are inserted after the MAC source address, but before the original ether type length or logical link control or LLC. The 1-bit CFI included a TR encapsulation bit for token ring frames can be carried across Ethernet backbones without using 802.1h translation. Adding a tag recomputes the frame control sequence. Figure shows how adding a tag in a frame recomputes the frame control sequence. 802.1p and 802.1q share the same tag. Adding a tag recomputes the frame control sequence. Native VLAN. Each physical port has a parameter called PVID. Every 802.1q port is assigned a PVID value called native VLAN ID. Default is VLAN 1. All untagged frames are assigned to the LAN specified in the PVID parameter. When a tagged frame is received by a port, the tag is respected. If the frame is untagged, the value contained in the PVID is considered as a tag, because the frame is untagged and the PVID is tagged to allow the coexistence as shown in the figure. For example, the 2 stations connected to the central trunk link in the lower part of figure, they are VLAN unaware, will be associated to the VLAN C because the PVIDs of the VLAN aware bridges are equal to VLAN C. Because the VLAN unaware stations will send only untagged frames, when the VLAN aware bridges devices receive these untagged frames, they will assign them to a VLAN C. Native VLAN. PVST+. PVST+ provides support for 802.1q trunks and the mapping of multiple spanning trees to the single spanning tree of 802.1q switches. The PVST+ architecture distinguishes 3 types of regions. a PVST region, a PVST plus region, a MST region. Each region consists of a homogeneous type of switch. A PVST region is connected to a PVST plus region by connecting two ISL ports. Similarly, a PVST plus region is connected to an MST region by connecting two 802.1q ports. At the boundary between the PVST region and the PVST plus region, the mapping of spanning trees is 1-to-1. At the boundary between the MST region and the PVST plus region, the ST in the MST region maps to one PVST in the PVST plus region. The one it maps to is called the common spanning tree, that is CST. The default CST is the PVST of VLAN 1 or native VLAN. All PVSTs except for the CST are tunneled through the MST region. Tunneling means that bridge protocol data units or BPDUs are flooded through the MST region along the single spanning tree present in the MST region. Integrated routing and bridging. IRB enables a user to route a given protocol between routed interfaces and bridge groups or route a given protocol between the bridge groups. Integrated routing and bridging is supported on the following protocols: IP, IPX, AppleTalk. VLAN. A virtual LAN or VLAN abstracts the idea of the LAN. A VLAN might comprise a subset of the ports on a single switch or subsets of ports on multiple switches. By default, systems on one VLAN don't see the traffic associated with systems on other VLANs on the same network. A virtual LAN or VLAN is any broadcast domain that is partitioned and isolated in a computer network at the data link layer or OSI layer 2. LAN is an abbreviation of local area network. To subdivide a network into virtual LANs, one configures a network switch or router. VLANs allow network to partition their networks to match the functional and security requirements of the systems without having to run new cables or make major changes in their current network infrastructure. IEEE 802.1q is the standard defining VLANs. The VLAN identifier or tag consists of 12 bits in the Ethernet frame, has the limit of 4096 VLANs on a LAN. Simpler network devices can only partition per physical port, if at all, in which case each VLAN is connected with a dedicated network cable and VLAN connectivity is limited by the number of hardware ports available. More devices can mark packets through tagging so that a single internet trunk may be used to transport data for multiple VLANs. Since VLANs share bandwidth, a VLAN trunk might use link aggregation and or quality of service prioritization to route data efficiently. To implement a basic switch not configured for VLANs has VLAN functionality disabled or permanently enabled with a default VLAN that contains all ports on the device as members. Every device connected to one of its ports can send packets to any of the others. Separating ports by VLAN group separates their traffic very much like connecting the devices to another distinct switch of their own. Uses. VLANs address issues, scalability, security, and network management. Routers in VLAN topologies filter broadcast traffic, enhance network security, perform address summarization, and mitigate network congestion. Switches may not bridge network traffic between VLANs, would violate the integrity of the VLAN broadcast domain. By using VLANs, the network can be easily split up. The host will not use that DHCP server and will obtain link local addresses or obtain an address from a different DHCP server. VLANs are data link layer or OSI layer 2 constructs IP subnets which are network layer or OSI layer 3 constructs. In an environment employing VLANs, a one-to-one relationship often exists between VLANs and IP subnets, although it is possible to have multiple subnets on one VLAN. VLANs controls the traffic patterns and react quickly to relocations. VLANs provide the flexibility to adapt to changes in network requirements and allow for simplified administration. VLANs can be used to partition a local network into several distinctive segments. A common infrastructure shared across VLAN trunks can provide a very high level of security with great flexibility for a comparatively low cost. In cloud computing, VLAN's IP addresses and MAC addresses on them are resources which end users can manage. Placing cloud-based virtual machines on VLANs may be preferable to placing them directly on the internet to avoid security issues. VTP VLAN Trunking Protocol or VTP is a protocol that propagates the definition of virtual local area networks or VLAN on the whole local area network. VTP carries VLAN information to all the switches in a VTP domain. VLAN Trunk Protocol or VTP reduces administration as a switched network. During configuration of a new VLAN on one VTP server, the VLAN is distributed through all switches in the domain. This reduces the need to configure the same VLAN everywhere. VTP is a Cisco proprietary protocol that is available on most of the Cisco Catalyst series products. VTP messages in detail. VTP packets are sent in either inter-switch link or ISL frames or in IEEE 802.1q.1q frames. These packets are sent to the destination MAC address 01-00-0C-CC-CC-CC with a logical link control or LLC code of Subnetwork Access Protocol SNAP, that is AAAA, and a type of 2003 in the SNAP header. This is the format of a VTP packet that is encapsulated in ISL frames. VTP packet inside 802.1q frame contains the ISL header and cyclic redundancy check, that is CRC, is replaced by .1q tagging. The format of the VTP header can vary based on the type of VTP message, but all VTP packets contain these fields in the header. VTP protocol version 1, 2 or 3. VTP message types. Summary advertisements. Subset advertisement. Advertisement requests. VTP join messages. Management domain length. Management domain name. VTP or VLAN Trunking Protocol maintains VLAN configuration consistency across the entire network. VTP uses layer 2 trunk frames to manage the addition, deletion and renaming of VLANs on a network-wide basis from a centralized switch in the VTP server mode. VTP is responsible for synchronizing VLAN information within a VTP domain and reduces the need to configure the same VLAN information on each switch. VTP minimizes the possible configuration inconsistencies that arise when changes are made. These inconsistencies can result in security violations because VLANs can cross-connect when duplicate names are used. They also could become internally disconnected when they are mapped from one LAN type to another, for example, Ethernet to ATM lane ELANs or FDDI 802.10 VLANs. VTP provides a mapping scheme that enables seamless trunking within a network employing mixed media technologies. VTP provides the following benefits: VLAN configuration consistency across the network, mapping scheme that allows a VLAN to be trunked over mixed media, accurate tracking and monitoring of VLANs, dynamic reporting of added VLANs across the network, plug-and-play configuration when adding new VLANs. As beneficial as VTP can be, it does have disadvantages that are normally related to the spanning tree protocol or STP, as a bridging loop propagating throughout the network can occur. Before creating VLANs on the switch that will propagate via VTP, a VTP domain must first be set up. A VTP domain for a network is a set of all contiguously trunked switches with the matching VTP settings, that is domain name, password and VTP version. All switches in the same VTP domain share their VLAN information with each other, and a switch can participate in only one VTP management domain. Switches in different domains do not share VTP information. non-matching VTP settings might result in issues in negotiating trunks, port channels, or VPC. WAN links. WAN link is a communication circuit that joins two or more local area networks, that is LAN, into a wide area network WAN. Many types of WAN links are possible between networks depending on the networking protocols and telecommunications carrier services used. But WAN links can be grouped into three broad categories. Circuit switched services. Dial-up connections that establish a temporary switched circuit through the carrier's telecommunication system for the duration of the communication session. When the connection is terminated, the carrier switches are freed up for other uses. One problem with this type of service is that the quality of communication varies between sessions with the quality of the switches and connecting trunk lines used. So circuit switched lines are often used as a temporary backup link in case the primary leased line goes down. Because circuit switched lines cost much less than leased lines, they are also used in low traffic WAN networking environments. These lines are typically point-to-point connections, but they allow users to dial any connection, not a single connection, as is the case with leased lines. Examples of circuit switched WAN links are modems and dial-up integrated services digital network, that is ISDN links. Advantage: less expensive. Disadvantage: call setup. Protocols: PPP, ISDN. Leased lines. Dedicated connections that establish a permanent switched circuit through the carrier system. They are always on and ready to carry network traffic. Leased lines are typically much more expensive than circuit switched lines because the carrier switches are dedicated to the customer even when they are not in use. Leased lines are typically point-to-point connections. Advantage: more secure. Disadvantage: expensive. Protocols: PPP, HDLC, SDLC. Packet switching can be either dedicated or dial-up connections to a public packet switching network such as X.25, a public frame relay network, or even a virtual private network, that is VPN, that uses tunneling over the internet. The switches for a communication send packet of data along the best route possible by using the logical address of the destination node. These are present in the header of each packet. Packet switching links can be either point-to-point or point-to-multiple-point connections, depending on how they are configured. Advantage: highly efficient use of bandwidth. Disadvantage: shared media across link. Protocols: X.25, frame relay. Cell relay. Similar to packet switching, but uses fixed length packets. Data is divided into fixed length cells and then transported across virtual circuits. Advantage: best for simultaneous use of voice and data. Disadvantage: overhead can be considerable. Protocols: ATM. Internet. Connectionless packet switching using the internet as a WAN infrastructure. Uses network addressing to deliver packets. Because of security issues, VPN technology must be used. Advantage: least expensive, globally available. Disadvantage: least secure. Protocols: VPN, DSL, cable modem, wireless. WAN protocols. Wide area networks evolved from the need to share data across vast geographical distances. The definition of WAN is a network spanning a wide geographic area. The purpose of the WAN is to connect local area networks or LANs and to transport data from one LAN to another. In our studies, the WAN is used much in the same way. WAN protocols have changed over time. At first, WAN protocols focused on error correction and were designed to operate on old, unreliable copper lines. WAN protocols today offer high-speed reliable transport on copper and fiber optic lines. Despite the vast evolution of the WAN, it still proves to be the slowest and most expensive part of any modern internetwork. WAN protocols function at the lower three layers of the OSI model. Some of the WAN technology protocols at the data link layer are HDLC, PPP, or frame relay. Some of the differences and similarities of these protocols are explored in the following sections. HDLC. HDLC stands for High Level Data Link Control Protocol. HDLC is a Layer 2 protocol. HDLC is a simple protocol used to connect point-to-point serial devices. For example, you have point-to-point leased line connecting two locations in two different cities. HDLC would be the protocol with the least amount of configuration required to connect these two locations. HDLC would be running over the WAN between the two locations. Each router would be de-encapsulating HDLC and dropping it off on the LAN. HDLC performs error correction like Ethernet. PPP, Point-to-Point Protocol, or PPP, is used for most every dial-up connection to the Internet. PPP is documented in RFC 1661. PPP is based on HDLC and is very similar. Both work well with connect point-to-point leased lines. The differences between PPP and HDLC are: PPP is not proprietary when used on a Cisco router. PPP has several sub-protocols that make it function. PPP is feature-rich with dial-up networking features. Because PPP has many dial-up networking features, so it is widely used as networking protocol. Some of the dial-up networking features it offers are as follows. Link Quality Management monitors the quality of the dial-up link and errors occurred. It can bring the link down if the link is receiving too many errors. Multi-link can bring up multiple PPP dial-up links and bond them together to function as one. Authentication is supported with PAP and CHAP. These protocols take your username and password to ensure that we are allowed access to the network you are dialing into. Frame Relay. Frame Relay is a Layer 2 protocol and commonly known as a service from carriers. Frame Relay creates a private network through a carrier's network. This is done with Permanent Virtual Circuits or PVC. PVC is a connection from one site to another site through the carrier's network. Configuration of carrier makes on their frame relay switches working properly. The benefits to frame relay are: ability to have a single circuit that connects to the frame relay cloud and gain access to all other sites. As the number of locations grows, we can easily implement the many circuits that are trying to fully mesh network with point-to-point leased lines. Improved recovery because request a single circuit to the cloud and PVCs to gain access to all remote sites. By using the PVCs, we can design WAN as we want. If the sites have direct connections to other sites, we can pay the small monthly PVC fee for each connection. Some other terms concerning frame relay are: LMI, Local Management Interface. LMI is the management protocol of frame relay. LMI is sent between the frame relay switches and routers to communicate what DLCIs are available and if there is a congestion in the network. DLCI, Data Link Connection Identifier. This is a number used to identify each PVC in the frame relay network. CIR, Committed Information Rate. This is the amount bandwidth you pay to guarantee you will receive on each PVC. Generally, you have much less CIR than you have port speed. You can, of course, burst above your CIR to your port speed, but that traffic is marked DE. DE, Discard Eligible. Traffic marked DE that was above your CIR can be discarded by the frame relay network if there is a congestion. FECN and BECN, Forward Explicit Congestion Notification and Backward Explicit Congestion Notification. These are bits set inside LMI packets to alert the frame relay devices that there is congestion in the network. Conclusion. In this chapter, we have covered the following in detail: data link layer function, switching process, Ethernet standard and its various frame formats, CAM table, hardware address or physical addresses, DTP, VLAN, VTP, VLAN routing, STP, WAN links, serial links, L2 WAN protocols, PPP, PPP authentication protocol like PAP and CHAP, frame relay and standard HDLC protocols.